All right, welcome back to the Explainer. Today, we're diving deep into group 17 of the periodic table. You might know them as the halogens. Let's jump right in.
You think you've seen family drama? Forget reality TV. The most intense, most dramatic family in all of science is right here on the periodic table. They are incredibly reactive, super powerful, and they have this strict set of family rules. Well, at least most of them do.
Okay, so let's get a proper introduction. Who exactly are the halogens? What makes them tick?
So the name halogen actually comes from Greek, and it means salt former, which, as you'll see, is a perfect name for them. Now, every single member of this group is a nonmetal, but the defining characteristic that really unites them as a family is that they all have 7 valence electrons, 7 electrons in their outermost shell. And that right there, that gets to the very heart of what drives them. See, in chemistry, the ultimate goal, the nirvana for an atom, is to have a full outer shell of 8 electrons. That's perfect stability. And the halogens, they are so close. They're just one single electron away. That makes them almost desperate to snatch an electron from literally anywhere they can find one. And that desperation, that is exactly why they are some of the most reactive elements we know of. Like a lot of families, the halogens have these predictable traits, these family rules that they all seem to follow. As you move down their column on the periodic table, you see certain properties change in this really orderly, predictable way. So let's look at the family rules. First up, reactivity. As you go down the group, from fluorine to iodine, they actually get less reactive. Kind of interesting, right? And the compounds they make with hydrogen, they get less stable when you heat them up. But here's the weird part. Their strength as an acid, when you dissolve them in water, actually increases as you go down. It's a bit counterintuitive, but that's the trend. These are the rules we expect everyone in the family to play by.
But, and this is where the story gets really good. Every family has that one rebel, right? The one who breaks all the rules. Well, in group 17, that rebel is fluorine. It's the very first member, the smallest, and it just completely refuses to play by the family rules. So what's the deal with fluorine? Why is it such an outlier? Well, it really boils down to a few key things. First, it's just tiny, incredibly small. Second, it has the strongest pull on electrons of any element in existence. We call that electronegativity. It's off the charts. Third, it takes a ton of energy to try and rip one of its own electrons away. And finally, unlike its bigger siblings, it doesn't have these extra storage rooms, these d orbitals, that would allow it to be more flexible in its bonding. Let's see how all this adds up to some serious rule breaking. Okay, rule break number 1, oxidation states. Because fluorine is the king of electronegativity, it will only ever take 1 electron. That's it. It's locked into a -1 oxidation state, period. Its siblings, though, like chlorine, they're way more flexible. They can show a whole bunch of positive states, especially if they're bonded to something even more grabby, like oxygen. But fluorine, nope, never. It's always -1. All right, remember that family rule we talked about? How acid strength is supposed to increase as you go down the group? Yeah, fluorine breaks that one too, big time. Its compound with hydrogen, HF, should be the weakest acid based on the trend. But it's not just weak, it's exceptionally weak. And the reason is fascinating. That insane electronegativity of fluorine creates these super strong connections called hydrogen bonds. The HF molecules basically just cling to each other so tightly in water that they refuse to let go of their hydrogen ions. And if you can't release hydrogen ions, you're a weak acid. It totally bucks the family trend. And really, this says it all. You might think all this rule breaking makes it an outcast, but maybe it's because of its unique properties that fluorine is the undisputed head of the family when it comes to raw power. It is, without a doubt, the most reactive of all the halogens and the strongest oxidizing agent there is. What does that mean? It means it's the absolute best at ripping electrons away from other elements. Okay, so that's the theory, which is cool, but let's see these elements in action, right? In the real world. We're going to use chlorine as our case study to see how we actually make it and what we do with it. So on a huge industrial scale, a common way to make chlorine is through something called the Dakins process. And the recipe is actually pretty straightforward. You start with hydrogen chloride gas, you mix it with regular old air, and then you pass that mixture over a hot catalyst. The result? Pure chlorine gas and a little bit of water. It's a really classic piece of industrial chemistry.
Okay, so we all know chlorine is in bleach, but have you ever actually stopped to think about what's happening on a molecular level when it zaps a stain out of your favorite shirt? It's probably not what you think. So here's the crazy part. The chlorine gas itself isn't actually what does the bleaching. Not directly, anyway. The first thing that has to happen is the chlorine reacts with water. That reaction creates this really unstable stuff called hypochlorous acid. And this acid almost immediately falls apart, and when it does, it releases a single superreactive atom of oxygen. We sometimes call this nascent oxygen. And that single lonely oxygen atom, that is the true hero of our story. It is so reactive that it just aggressively attacks the molecules that make up the stain. It breaks apart the chemical bonds that are responsible for the color. This whole process is a type of oxidation, and because it fundamentally changes the stain molecule forever, the bleaching action is permanent. The color is gone for good. Okay, things are about to get even weirder. What happens when these super intense family members decide to bond not with other elements, but with each other? Well, you get some really interesting, really unusual compounds. These are what we call interhalogen compounds, and they follow their own little set of rules. Rule 1, it always has to be two different halogens. Rule 2, the bigger, heavier halogen always gets to be the central atom. And, of course, what does that mean? It means tiny little fluorine can never be in the middle. And finally, just like their parents, these compounds are also really powerful oxidizing agents. And the variety here is pretty cool. You can get a simple one-to-one compound like chlorine monofluoride, or you can get something totally wild like iodine heptafluoride. Just picture it, one big central iodine atom getting absolutely swarmed by 7 tiny, super aggressive fluorine atoms. You ready for another classic fluorine moment? Another anomaly? Check this out. When halogens bond with oxygen, pretty much everyone else gets a positive oxidation state. Why? Because oxygen is the second most electronegative element, so it usually wins the electron tug-of-war against guys like chlorine or iodine. But who's number 1? Fluorine. So even when it's bonded to oxygen, fluorine still wins the fight. It holds onto its electrons and keeps that signature -1 state. Okay, one last example that really shows how unique fluorine is. Let's talk about oxoacids. Those are acids that have hydrogen, oxygen, and a halogen. Chlorine is a champ at this. It can form 4 different kinds. Bromine and iodine can make several too. But fluorine, it can only form a single one, this really unstable thing called hypofluorous acid. So once again, while the rest of the family is showing off all this versatility, fluorine just does its own thing. So, we kind of end up right back where we started, don't we? With this question, what happens when the smallest, most reactive element just refuses to play by the rules? Fluorine's refusal to conform isn't just some weird quirk. It's what literally defines the upper limits of reactivity in all of chemistry. It's a powerful reminder that even in a system as beautiful and orderly as the periodic table, there's always an exception. And that exception doesn't just break the rules. It helps us understand why the rules exist in the first place.